Hey there, welcome to Learning Labs. Today we're in Geology 7. We're talking about 3.7.2, which is all about minerals and mineral resources. All right, let's jump right in. What is a mineral? Well, a mineral is a chemical element or compound that is naturally occurring and has crystal-like structure. Okay, a rock is a natural material that is made up of one or more minerals. Okay, mineral is the basic form. Rock is something made up of multiple minerals. Okay, here we got some examples: sulfur, gold, and diamond. Some of my Minecraft guys out there know exactly those are minerals. Quartz is a mineral compound. All right, mineral resource. What does that mean? Well, if you attach the word resource to it, it just means that it's something that humans can use for a specific purpose. Check out this little dude here, riding his roller skates. On the human body, we have a bunch of minerals. Check out this guy's arm. He's got a gold ring. We got his zipper, which is made up of copper and zinc. Okay, we got his roller blades. That is iron, chromium, nickel, aluminum. Even the watch, we got nickel, tin, carbon, copper. Really cool stuff. All over us is a bunch of minerals. How do we identify minerals? Well, check this out. Let's look at crystal structure. All right, you have hardness, which is the important property of minerals. It's a measure of minerals' resistance to being scratched. Okay, diamond, my Minecraft guys out there, shout out to them once again. Know that diamonds is the hardest material. You have luster, which is gold and silver, and they appear shiny. Okay, it's about the shininess. Usually people go crazy over the luster. They want that shiny gold, a shiny chain, whatever it is, right? Check this out. That looks crazy. That is a galena, and it's got a cubic crystal structure. Here in Canada, this is where you can find certain types of minerals all across the country. Notice where obsidian is. It's on the coast, right? By the Ring of Fire, where the volcanoes. All right, 3.7.2, how rocks are formed. So there's three rock families: igneous, sedimentary, and metamorphic. Let's start off with igneous. It forms when hot magma or lava cools. So it came out the volcano, boom, went out everywhere, and then it cooled off in the cool atmosphere. It becomes igneous rock. Magma is melted rock found deep below Earth's crust. So if you think about magma, magma is when it's still in the ammunition chamber. Okay, it's not out of Earth yet. And then once it explodes, it shoots everywhere. Then it becomes lava. Okay, it's just a terminology so that people know what you're talking about. Are you talking about lava when it's in Earth, or are you talking about when it's outside of Earth? Okay, that's the difference there. All right, igneous is classified by rock formed above or below. So you have magma and you have lava. You also have intrusive igneous rock and you have extrusive igneous rock. So was it inside Earth, intrusive, or is it outside, extrusive? So check out this one. Oh, I don't got no zoom. Okay, we'll jump into this first. So the rock cycle, it just means that a rock, if it's igneous, it's not subject to staying igneous its whole life. Now, rocks live forever, as you know. Living forever means you get to change forms. So first, you might start out as magma down here, and you become an igneous rock. You left the Earth, the inside of Earth, and you're on the surface, you cool down your igneous rock. Over thousands of years of harsh weather, acid rain, whatever it is, people kicking rocks, you become sediment. And then over 1,000 more years, a whole bunch of pressure, maybe dinosaurs are stepping on you, more pressure from the atmosphere, you become compact, you become sedimentary rock. And then over 1,000 more years, more pressure, maybe you get pushed back into Earth and you get heated up, you become metamorphic. The meta means within, between. And then you go further into Earth, maybe you even touch the core. Wow, I made it to the core, and you melt. You turn back into magma. And you come back out through the volcano, and now you're back as igneous rock. And here, this picture I wanted to show you, this is intrusive rock here. So it did not leave the inside of Earth. Earth's surface is here. It did not leave. So it's intrusive. It's inside Earth. And then you have extrusive, which did leave. Sedimentary rock is loose material. Think about sand. Process of squeezing together layers of sediment called compaction. Okay? Cementation is a process in which pieces of sediment are held together by another material. So check out this example. You can go outside now and show your parents that you know different types of rocks, because when you see sediment, you want to see these striations, these layers. Those are individual time capsules. So one layer is made, 100 years later, another layer is made. And it's pushed down and pressured, stuck together by either another material or through pressure and compaction. Now check this out. This is how it forms over hundreds of years. Cementation versus compaction. Metamorphic, okay, with a lot of shiny micromaterials and many layers. They're made when heat and pressure or fluids change one type of rock into another. So it's the middle ground between switching from sedimentary to igneous. It's got to be a middleman. You can't go straight from there to there. You got to have the middleman. The middleman is metamorphic. All right, they're always formed below Earth's surface, okay, because you need that heat and the pressure. That's what breaks it down from sediment into metamorphic. All about moving crust of Earth. 3.8.1, which is all about weathering and the rock cycle. So what is weathering? Weathering is the breaking down of rocks into sediments. Okay, you recognize we talked about metamorphic, we talked about sediment. How do you get to sediment is through weathering. Two types of weathering occur, mechanical and chemical. Now, if you remember from our body systems unit, mechanical or physical change is reversible. So it's like crumpling up a piece of paper with your hands or chewing food. It can be reversed. Even though it's nasty, you can uncrinkle the paper and you can slowly put the food back together. But once it changes through chemical, so like your enzymes, your saliva, chemically changing the chemical makeup of that food, and acid rain or maybe fire burning the paper, we cannot change it back. And it has changed chemically. So the fire burning the paper has changed it from paper to ash and cannot be changed back. Whereas crumpling it, it's still paper. After it's crumpled, it just looks a little bit different. So mechanical weathering in terms of breaking rock down is like growing plants, which the roots break the sidewalk. I don't know if you ever seen that walking on your way to school, or expanding ice. If water gets into the cracks and expands as ice, the rocks will crack. Chemical weathering, on the other hand, is dissolving materials like acid rain or changing the chemical composition. So if you look at the example here on the, the right side, the Lady of Liberty used to be like a bronzish color. However, over time, chemical weathering has changed its color and its and its chemical composition to be green. You have over here, check out this rock on the left. It wasn't like this always. It used to be a pyramid shape. However, over time of heavy winds and sandstorms, it deteriorated, physically worn down the rock to show only the strongest pieces that are left. The loose sediment has been washed away through mechanical weathering. Another type of mechanical weathering is landslides. Okay, a bunch of examples here. And if you're in BC, this is a little bit dangerous. This happens a lot. Water from rain soaks up the soil. Soil becomes loose and goose, and it slips down and becomes a hazard. All right, let's jump into 3.8.2, which is all about the crust and the clues that exist within them. First, let's go over some terms that you need to know. Cross section, which is a drawing or diagram where you see an object and its inside. Let's jump into the first cross section of the ocean floor of Earth. So here we have some terms. Ocean ridge, which is a long mountain range on the seafloor. You can see it right in the middle. The continental slope is a deep slope on the seabed, which connects the continental shelf and the sea floor. The continental shelf is a shallow underwater ledge located between a continent and the deepest of the ocean. Abyssal plain is a large flat area on the seafloor, just like the Prairies Plain of Canada. A rift, this one's cool, is the opening of the oceanic crust, where molten materials from Earth's mantle can escape. All these features provided clues on how Earth's crust moves. Now we're gonna jump into how it actually moves. Take a look at Pangea. Y'all probably already know about Pangea because you're a bunch of geniuses. It's a scientific theory that all continents were joined together in a huge landmass called Pangea at one time. The theory of continental drift is about the continents changing positions very slowly and moving over the surface of Earth a few centimeters per year. So let's take a look at what it used to look like. Here, 250 million years ago, Pangea, one large landmass. This is where the dinosaurs were. 135, they started to split apart. Remember, the landmasses, continental plates, are sitting on the lithosphere and the asthenosphere, which is like water. And the boat's on water, as me and my broski were on the kayak, and we start to float away because the current underneath is moving. And then here we are, present day, it's still moving, it's still spreading apart. What do you think is going to happen if it keeps moving in its direction, right? It looks like it's moving away from each other, but you're on a globe, you're on a sphere. So if it's moving away this way, what happens on the other side? I don't know. Here's some clues. Fossil evidence. The Mesosaurus, which is in the blue, it's hard to see. Let me zoom up here. Mesosaurus, it's in green. It's in South America, over here on the coast, as well as on Africa. Now, how can that happen? Because these dinosaurs ain't swimming. The only way this is possible is if we go back here to Pangea and we see that South Africa used to be connected to Africa. There used to be no water between them. So that way the dinosaurs were moving between the two and they may have died on both sides. Moving on to today, you see in South America and Africa, they're very far away. Therefore, the fossils are far away. Same thing with Australia and Antarctica. You can see that the Glossopteris fossils are both found there. And the Lystrosaurus, both found on Africa's very southern tip and Antarctica's northern tip. You have some more evidence from rocks. Okay, so fossils as well as rocks. You have the same types of mountain ranges existing on continents that are very far apart. All right, so more evidence exists in the seafloor spread. So what are we talking about here? Seafloor spreading is just what it sounds like. The seafloor slowly increasing its size because of formation of new crust. So like how land forms on the surface of Earth, underneath the water, there's volcanoes that erupt, allowing magma to surface, becoming lava, and cooling off in the cold ocean. When it cools off, it creates new crust and becomes the rift and the oceanic mountain ranges. What do we call those? Ocean ridges. And that's where we find it. The seafloor spreading indicates how the land masses are being pushed in certain directions. Advances in technology also allow us to find new clues like sonar, which is a device that sends out sound waves and then records the time that waves take to travel back. Ships use that to navigate the seafloor. Seismic waves used to study the seafloor. Energy waves are created by explosions. Air guns used by ships. I don't know if you've ever seen in King Kong, when they first arrive on the helicopters, they start throwing these seismic bombs.
Fox leader to Fox group. Split up. Survey your zones. Fox 7, put Lancet on deck.
Copy, Fox leader. Fox 3 headed to zone 6.
Put us down over there!
Everyone else, stay with the team leader.
Check here, George, 3 o'clock. Let's move it!
Ready for seismic charges.
Roger that. Fox group, let it fly.
Copy all, Fox 3, heading 090.
You seeing what I'm seeing?
The seismic response is incredible.
Hey, Randy, you're not gonna believe this. The bedrock?
It's practically hollow.
And it's to detect what's going on underneath the land. It's this kind of sea below the surface of the earth. However, the seismic waves are super loud, and as you can imagine, pissed off King Kong pretty badly. Just like that, it will really hurt an ecosystem if you continue to use something like that. Okay, a core sample is another way of looking what's inside Earth. It's like digging a cylindrical tube and then raising it up and then seeing the layers of what's going on underneath there. And that's usually to help us find oil. Here's a map of the ocean's ridges and sea floors. You can see that some trenches exist where we have not yet discovered. So we had the continental drift theory. Now we have the theory of plate tectonics. This is the most updated theory. The theory proposes that plates on Earth's lithosphere, interact with each other. Tectonics is a study of movement of large-scale structural features on Earth's crust. Now you have three types of boundaries here between the tectonic plates. You have convergent, converge. Converge means to come together. Plates that move together towards each other and collide. Divergent, like divide, spread apart. Plates that moving away from each other. And then transform boundaries. These ones that slide beside each other. Okay, so that's the three ways that plates can interact with each other. Here are the plates of the Earth. You have North American plate, which you have the Juan de Fuca plate that is about to mess everybody up because he's slipping and he's submerging beneath the North American plate. You have the South American plate, Antarctic plate. All right, let's talk about convergent boundaries. So there's three types of converging boundaries, but you have ocean to continent, you have ocean to ocean, and you have continent to continent. So ocean to continent means you have an ocean plate and it's going to converge to a continent plate. What happens here? The oceanic plate sinks beneath the continental plate, creating a subduction zone. Okay, subduct means to go underneath. Why does this happen? Because the oceanic plate is heavy, it's dense. So the denser material slides underneath the lighter material. This is a heavy sinking boat, and this is a lightweight, maybe flower or something floating on the water. The boat will sink underneath it. Okay, this creates deep sea trenches. Ocean to ocean is both dense, but the older and the colder one, denser one, will bend and sink. New crust formed as magma rises to make volcanoes, also creates deep sea trenches. Okay, and then you have continent to continent, which is a colliding and crumpling up. So none of these guys submerge, they just crumple and crash out. It's crazy. This is the one that creates mountains. Volcanoes do not form here because when you slide two of them together, they just crash into each other and create mountain ranges. Okay, and there's no subduction zone. So here we have a rift valley. So continentals are moving away from each other, splitting open, allowing magma to rise, maybe creating a volcano. Then you have over here this subduction zone. That means a plate is going beneath and another plate going on top. You have mountains being created here because you have a subduction zone here pushing on this plate, which crumples it up slightly, creating mountain ranges. Let's keep it moving. Over here in the ocean, you have diverging plates creating ocean ridges, allowing magma to seep up, creating new sea floor. And then over here you have another diverging plate. It's converging, creating a deep sea trench, allowing volcanoes to form and mountain ranges. Measuring plate movement. So how do we measure all this cool stuff? Earthquakes, volcanoes, and mountain ranges are evidence of plate movement. Scientists use satellites and laser technology to measure the exact movements of the plates to the nearest centimeter. So check this out. This is the Juan de Fuca plate, and it's creating a subduction zone between the North American plate. This is the guy that everybody's worried about. He's causing all the trouble because he needs to move in the last 50 years to release some of that pressure. You can think about it as a rubber band being held. The farther you go, the more it's going to hurt when I release. It's being held for too long, and we need to release some of that pressure. And if we don't release enough pressure over the next 50 years, it's going to snap and everybody's dead.